so I'm glad not to be following the president. So this is about the BGP Monitoring Protocol, which is joint work with a number of folks and is currently a draft in the IETF GROW working group. So just to get right down to the meat, what is this thing? And some of you may have seen previous iterations of this work, and I'm going to do a little history in a few slides. But the idea with BMP is that we saw a need for there to be some way for a monitoring station to get all the routes off of your router, not just the active paths, not just an initial dump, but the initial dump plus incrementals in real time, and to be able to do it without screen scraping the output of a show route for a whole number of reasons, including the fact that that's a pain, including the fact that it's resource intensive on the router, including the fact that it's just silly. And what is this useful for? Well, obviously and clearly, looking glasses, network analysis. Since we published this thing, it seems like people are interested in using it for more things as well. So again, I'll get to history in a second, but there's some basic design goals that have motivated what the draft has morphed into, and that is to keep the design simple, to make sure that while keeping it simple, we're still providing something that addresses the need. This kind of goes with the first bullet. It needs to be easy to implement. And finally, and I think this is important, it needs to be non-service affecting. And it's always kind of a lie when you say something that's sharing CPU with your regular routing is completely non-service affecting. But the idea is that this is the monitoring needs to get out of the way when you need the CPU to do actual routing on your network. So some of you with long memories that extend back more than 6 months, the way mine seems to, will maybe say, haven't I seen this movie before? And yeah, there was a 0.0 version of the draft submitted way back in 2005, which turned out, although to be not sufficiently cooked. And by that I mean, it was sort of a paper design, sat down, said, okay, here's some design points. And there was one critical design point that turned out to be wrong, and that was, and I'm kind of jumping ahead here, but that design point was to say, okay, we want to give you a bit-for-bit clone of the inbound update stream. So what we tried to do in that draft is, or what I tried to do, is to say, for every peer, I'm going to clone exactly whatever routes that peer sent me, whatever came in on port 179. I'm going to send that out to the monitoring station with complete fidelity. That turned out to be too ambitious, and actually in the event when you sit down and try to figure out the implementation, you say, oh, this thing is never going to scale. And as a result, the whole work just got shelved. But it turns out that people actually still want to be able to get the routes off of their router. And we saw quite a bit of interest in this and said, okay, fine, let's take it, dust it off, keep the high order bit, meaning keep the design goal of being able to get the routes off of your router, get all the paths, not just the actives, throw out all the other assumptions and start again, which is what we've done. And critically, we actually have an implementation running in the lab, so this time we know that the trade-offs are correct. Some people have asked why this thing, once you actually sit down and read through the draft, looks a heck of a lot like BGP. Why aren't you just using BGP for this? And there's one very simple answer that is probably evident to the majority of the people in this room, which is that BGP just gives you the active paths. That's the way BGP works. If I send you 10/8 and then I send you another update for 10/8, that is an implicit withdrawal of the previous one. We don't want to give you just the actives. We want to give you all the paths. Therefore, we need something different. There's a thing called add path that I thought we were going to have a talk on later in the NANOG, but I guess not. That does change things. So why not use that? And the answer is, yeah, the add path extension actually probably can do most of what BMP does, and certainly, at the very high level, will give you the same, can give you all paths. But it's got a number of drawbacks. One is, or let's do this the other way and say, what does BMP give you? And it's it's carefully designed, in fact, to be very, very cheap to implement. In terms of memory, it's always, you always get yourself in trouble when saying this, but it's essentially free. The overhead is like a bit per path. You can do it, or at least in our implementation, we found that we could do it basically non-invasively. The code path that gets executed if you don't turn on BMP it's just the same old code path that it ever was, with the exception of like 3 entry points or something. It provides some other little convenience things that I'll talk about in the next few slides. I guess that's it. Okay, so I'm not going to give you all the details, certainly not packet cartoons and so on. The draft is there to be read if you want that level of detail, and I very much encourage you to read it. But the overview of how do you use this thing and what happens is on your router, you configure the identity of your management station, which simply is the address and port number that station is going to listen on. And then optionally, an implementation can let you filter and only monitor a certain set of peers. Ours currently gives you all routes for all peers. And then what happens once you've done this configuration is the router will start trying to connect to that port on that management station. Once it gets a TCP connection, it sends you an initial dump of routes in a very similar way to what you would see over a regular BGP connection, only of course you're getting all the routes for all the peers. And the way these routes are sent is they're formatted in regular BGP updates. They're then wrapped inside an encapsulation. And the encapsulation, actually I'll talk about it on the next slide. And then ongoing, once you've got the initial dump done, you get incrementals as peers advertise and withdraw routes. They turn into advertisements and withdrawals that are propagated again inside the same encapsulation. Okay, and the encapsulation is pretty simple. It basically tells you who the peer is and when the route was received. So and identity of the peer means the address that you're actually peering to, the BGP identifier, the RD if that's applicable, route discriminator that is, and the AS number of the peer. And the timestamp is the time that the route was installed on the router that's being monitored. So, if I receive 10/8 at time T, and then at some future time I finally get around to sending that to the monitoring station, I'll stamp it with time T. The encapsulation gives you granularity up to microseconds. Our implementation doesn't give you actually that much resolution, but it's available if an implementer wants to use it. Okay, so as a sidecar, we've also got these statistics reporting messages that they're optional to implement because they're not the base bread and butter of getting you the routes, but it seemed useful and easy to include, so we went ahead and did it. And right now there's a few counters defined: rejected prefixes, duplicate prefixes, duplicate withdraws, and then cluster and AS path loops. It's extremely easily extensible. It's just a TLB structure. There's a big code point space, so there's not really any impediment to adding favorite counter of your choice. You also get notifications when a peer goes down. Again, the picture here being you've got a router, it's being monitored, it's peering to 20 different peers, and then a monitoring station getting routes for all those peers. So if peer number 6 goes down, the router puts together a peer down notification message and says, hey, by the way, peer number 6 went down, and here's the notification information I have for it, if any. If peer 6 just closed his TCP connection and went away, then there's not much notification to be had. Okay, so the kind of operational characteristics of this thing are, as I alluded to earlier, the BMP updates. One thing that you can't assume is that they're absolute bit-for-bit clones of the received updates. But with that said, instead they're regenerated by following virtually the regular BGP update generation code path. The big difference being that instead of pulling the data, if you remember, sort of BGP conceptual model, normally you've got, your routes come into the address bin, then they go through policy, they go into your local rib, and then they go through some more policy and they go into an address out, and then updates get generated out of that, or at least that's the block diagram version of it. In this, we're kind of short-circuiting away the local rib and the address out, and we pull the data directly out of the address in. What that means is that if you've applied policies that change the route, for example, you strip out communities, or you change the local pref, or whatever, that does not get reflected in the update that gets pushed out to the monitoring station. So the idea being that although you don't get 100% fidelity, you get pretty good fidelity of what the received update looked like. Here's my best picture that I'm able to give to you of how I received the update from the peer. Second implication of this is that the updates, you don't have a guarantee that if you receive 1 million updates from your peer, you're going to generate 1 million BMP updates towards your monitoring station. If your peer sends you, announce 10.8, withdraw 10.8, announce 10.8, withdraw 10.8, announce 10.8, withdraw 10.8, at some point there's going to be some state compression, and the router's going to say, look, you're jabbering at me. I'm just going to send the final state of that route to the monitoring station. The BMP does share with BGP, though, the characteristic that when things calm down, the monitoring station will converge to have, to know what all the current routes are on the monitored router. In terms of implementations that exist, this is the one that's in our lab, and it's almost embarrassingly simple. That's all the configuration there is. Who's the monitoring station, and then the stats timeout line is, how frequently should I generate these stats counters to you? I'm told that there's a Quagga implementation underway. A number of other people have talked to me about clients that they're thinking about doing, but these are the ones that I'm able to share on a slide. This is going fast. Okay, we've had, after this was presented at the IETF, some conversation that's gone on already. One request that we've had was to reintroduce what existed in the earlier draft called the L bit, which was an indication, a flag to indicate whether a route that's been sent to the monitoring station is pre or post policy. And by that I mean, remember I said a minute ago that we were pulling all the routes out of the address bin. So they were sort of the uncooked pre-policy routes. If your implementation, for whatever reason, is not able to do basically soft reconfig, you don't have the ability to retrieve those pre-policy routes, you still want to do BMP, you might have to resort to pulling the routes out of your local rib post-policy. And there was a request to say, look, please tell me, is this route pre-policy or post-policy? Seemed reasonable. It's not hard to add to the implementation, so we'll probably put that in the 01 draft. Another request was to say, look, you've got a peer down indication. You don't have a peer up indication. I can guess pretty well by seeing routes from peer that peer is up, but I might have some peers that send me no routes, and then they'll be invisible. So please give me a peer up indication. Again, seems reasonable. Shouldn't be hard to implement. We'll probably add it to 01. I hope that some of you will take a look at the draft and send any further comments that you have. So just to kind of pull this together, sum up, we've got a thing. Let's a management station pull routes off of your router. Gets you a full dump, the same thing that you would get out of show route, only in a more elegant fashion. It looks a whole lot like BGP uses the BGP code path to regenerate the updates towards the monitoring station, and also provides some convenience counters. It's really not suitable for use as a routing protocol for reasons I haven't gone into here, but I could do offline, I guess. And finally, we have an implementation that's working in the lab, and I believe will be in the field sometime this year. The real reason that I'm standing up here and talking to you is that this is really a prime time for operators to take a look at this, think about, do I have a need that this meets? Maybe more importantly, do I have a need that this almost but not quite meets? And if you only gave me this one little feature, then I could really make effective use of it. Because we haven't. It's still in draft. The software is in the lab, but not yet in beta. So, really good time to try to make changes. I think sometime later this year, I think we'll try to advance the draft to RFC. So now would be a very good time to take a look, think about whether you have needs, send feedback either directly to the authors, we're on the slide number 2, or to the GROW mailing list. And with that, thanks very much, and got plenty of time for questions, I believe.
Hey, John.
Okay.
Dave Meyer. Hey, first off, I want to thank you for doing the fine work. We need this. I've been in the route collection business for a while, and one of the big problems we've always had is that the fact, I think you said this a couple times, basically, you have a distributed instrument when you're trying to do this in today's world, and the sending side of that instrument has a really heavy filter on it. We call it BGP best path. And it basically wrecks the data you get out of the instrument, or it puts a heavy bias on it.
Yeah.
And so as a result, what we wind up doing is going all over the world and trying to find different places in the topology where that filter hasn't yet been applied.
Right.
So while you're talking about, it's almost impactless on and all the local stuff, it's actually going to have an impact on the global routing system, because we could change the way that we do route collection if we have this technology, which overall, in aggregate, will cut down on the number of route collection TCP sessions, or whatever you want to call that, right?
Ooh, that's good news.
Yeah, if you think about it a little bit, because basically, the problem we have now is, the old graph theory thing, the graph looks different from where you are in the topology, so if you want to get a good view of the graph, you go all over the place, right? So that's a really big benefit. The question I wanted to ask you was, what kind of state requirements? I know you said 1 bit or something like that, and I read the draft a couple times, and I wasn't really sure. A lot of this might be implementation dependent, but maybe you could talk about your implementation. What state requirements BMP puts on the router, and where the scaling factors are? Like, is it in the number of routes and the number of sessions, or what? You know what I'm asking, right?
Yeah. So basically, I should have had this on a slide. There's one constraint we've put in our implementation that really helps a lot with scaling, and that is you get one collector. And then if you want to have multiple guys collecting off the same router, you need to do fan out from the collector rather than from the router itself. That means you only need to manage state for the one collector, and that means that you get to basically the only state you need to know is, did I send this route to the collector yet, yes or no, which amounts to a bit worth of state per path.
Does it mean that does that constraint mean that you only have to have enough, you only duplicate the amount of output buffering you have by one time, or something like this? Is that what you're after there?
Yeah, it's more than that, actually, because BGP implementations don't really do output buffering very much. What they really do is they do internal bookkeeping in the database to decide whether they've they
Sure.
need to generate an update or not. It's,
Sure.
it's sort of virtual buffering, I suppose, if you like.
Right. Somebody has to do the bookkeeping, is all I'm saying.
Yeah, and so you save a whole bunch of queue structure stuff that, I mean, for a full-on BGP implementation, you have to keep a separate queue per peer group. You don't have to do that because you've already got, at least our implementation already has a time-ordered queue of updates or of paths, and then you just need the one bit to sort of tell you whether you need to generate an update out of it or not.
Thanks.
You're welcome.
Hey, Dave, if you don't mind not sitting down for a second. Todd Underwood, Packet Fabric. So the question I have is, so the Junos, not surprisingly, and Quagga, not surprisingly, but not all that relevant. And then Cisco? Have you talked, is anyone at Cisco interested in this implementation?
Yeah, my badge says Juniper, so
I
can't
know,
answer.
well, I was, but then Dave stood up to ask a question, so I thought I'd. Is anyone at Cisco interested?
Let me just be straight about this. I haven't talked to anybody about it in Cisco, but I'm going to go push on it. That's all I can say. I mean, it's like, yeah, there's Cisco J. Okay, well, everybody knows that, right? But I haven't done anything about it,
Okay.
and nothing's going to happen unless somebody does something about it.
Okay, thank you.
I suppose this is the time to also say, talk to your account team, et cetera, et cetera.
That would be the best one.
They can help Dave.
Yeah, they can definitely help.
Quick similar thought along the same lines. Have you talked to KC at CADA?
No, but that's a very good suggestion.
Pictures of this would engage people's attention.
That's a great idea.
Ann Johnson from XDR.
I'll drop her a line. Thanks.
Sriram from NIST. Have you thought about the loading on the route processor if it's going to run on a lower priority compared to BGP itself?
In our implementation, it in fact does do so. So, I mean,
Especially when BGP session is recovering after a
yeah.
failure.
Is your question what the behavior is during stress on the route processor?
Yeah, if it would have an impact on update processing, for example.
Yeah. So this is where I had that bullet that said, we've tried to make it non-intrusive and we've tried to make it non-service affecting.
Okay.
And the approach to that is basically run it at a lower priority, as you say. The consequence is that during times of high routing stress, your monitoring is going to lag your routing.
Or you may miss some messages as well.
You'll never desynchronize with the router, but you may see message compression the way I referred to a few slides back.
Okay. Thank you.
You're welcome.
If you have Martin Levy, Hurricane Electric, you talked about only having it configured for one collector,
Right.
for this one bit efficiency. Does that mean we start having a fight in the community between Oregon and CADA and Renesys and anybody else that wants this data?
I hope not. It ought to be fairly easy to take whatever beefy cheap PC you want, have that be a proxy, and then have it fan out the update stream to as many different collectors as you like. But so you can finesse the fight that way. The reason that it's easy to do that, and it's not at all easy to do that with real BGP, is that the communication is unidirectional in this case. The router just pushes stuff at the collector and never expects to hear anything back. So yeah, you can basically cobble this together with NC and not much more.
Tom Daly, Dynamic Network Services. So on the collector side, in terms of implementations, establish a TCP socket and start listening, and that's all you need.
That's exactly right.
Okay.
You then need to be able to parse BGP messages, but
Sure.
there's a whole lot of open source code out there to do it.
Sure. Thank you.
You're welcome. Thank you very much.